If I asked you who first proposed the idea of a black hole, who would be your first guess? Perhaps Albert Einstein, Stephen Hawking, or Carl Schwarzschild. While these scientists have had a huge impact on black hole astrophysics, the idea of a strong gravitational field altering light was first described by an often overlooked clergyman named John Michell. John Michell was the first to describe an object whose escape velocity exceeded the speed of light, which they called dark stars. The year was 1783. Falling very close to the midpoint between Newton's theory of universal gravitation and Einstein's theory of special relativity. John Michell, a retired professor of geology at Cambridge, was working as the rector of Thornhill in England, and he used his spare time to fuel his scientific curiosity, in particular, working with theories of light and gravity. John supposed that light consisted of a particle, which was a topic of hot debate at the time, and that gravity acted upon the particles of light in the same way that gravity acts on all objects. At the time, there was no experimental evidence to think otherwise, and Newton's gravity was considered a universal law. Rector Michell reasoned that objects within a gravity well require a certain amount of speed to reach infinity, the speed which we now call escape velocity, and that for particularly small and dense objects, the escape velocity might exceed the speed of light. The French mathematician Pierre-Simon Laplace came up with the same idea in 1796, which he referred to as an invisible body. Although Laplace first wrote about invisible bodies in 1796, more than 10 years after Michell, this idea was probably developed independently, since there was very little scientific communication between France and England in that period. Let's have a look at the escape velocity equation again, but this time let's do something silly. Instead of solving for the velocity, VE, let's solve for the radius of an object with mass m, whose escape velocity is equal to the speed of light, just as Rector Michell did. We'll denote the speed of light as the letter c and use it to replace VE. In order to solve for the radius r, we need to first square both sides of the equation so that c becomes c squared and the square root sign on the right-hand side goes away. And then we can multiply both sides of the equation by a factor of r divided by c squared, leaving us with the solution in terms of the radius. A body of mass m has an escape velocity equal to the speed of light when its radius r is equal to 2gm divided by c squared. So what this means is that an object of mass m, we can calculate how small it would need to be in order to have an escape velocity equal to the speed of light. Let's try Earth's mass for fun. Inserting m equal to 5.972 times 10 to the 24 kilograms into the equation yields a radius of a puny 8.87 millimeters, like a tiny ball less than 1 centimeter on a side. So if a ball weighed the same as the entire Earth, it would have an escape velocity equal to the speed of light at its surface. Our sun's escape velocity is 617.7 kilometers per second, given a solar mass and the average solar radius. In order for the sun's escape velocity to increase to the speed of light, or 300,000 kilometers per second, its radius would have to be reduced from 695,700 kilometers to a radius smaller than 2.953. What would the sun look like if it were compressed to 2.953 kilometers? With its escape velocity equal to the speed of light, light would no longer escape from it, so the sun would appear dark. Also, any light falling towards the sun would disappear completely the moment it crossed the sun's dark surface. In fact, nothing could escape from the object's surface because we know that the speed of light is an upper limit in our universe. Using only classical physics, Michell was the first to describe dark stars by trying to determine a method for measuring the distance and brightness of stars. Instead, he invented the first description of a black hole, an object massive enough to prevent light from escaping it. Additionally, Mitchell also predicted one of the most interesting results in black hole physics. You see, the equation that we naively replaced escape velocity for the speed of light, well, that equation comes up again once we encounter Einstein's general relativity as a solution for the event horizon of the simplest kinds of black holes, Schwarzschild black holes.